Section 8.8, Improper Integrals. In defining a definite integral from a to b f of x dx, we dealt with a function f defined on a finite interval from a to b. And we assumed that f does not have an infinite discontinuity. In other words, f of x goes to positive or negative infinity as x goes to c from the right or the left. Now we extend the concept of a definite integral to the case where the interval is infinite, and also to the case where f has an infinite discontinuity in the interval from a to b, the closed interval from a to b. In either of these cases, the integral is called an improper integral. Now let's consider the infinite region S that lies under the curve y equals 1 over x squared, which we know looks like this. And it is above the x-axis and to the right of the line x equals 1. Since S is infinite as x goes towards infinity, you might think that the area is infinite. So if we look at this, the area from 1 to t of 1 over x squared dx is negative 1 over x evaluated from 1 to t, which is the negative of 1 to t minus a negative 1, which is 1 minus 1 over t. Notice that the area is less than 1 no matter how large t is chosen. Now, as t goes to infinity, in other words, the limit as t goes to infinity of our area is equal to the limit of 1 minus 1 over t equals 1. So the area of the infinite unbounded region S is equal to 1, and we can write that the integral from 1 to infinity of 1 over x squared dx equals the limit as t goes to infinity from 1 to t of 1 over x squared dx, which is 1. That is really amazing. In conclusion, we define the integral of f, not necessarily a positive function, over an infinite interval as the limits of integrals over finite intervals. The first basic type of integral we will look at is one in which either one or both of the limits of integration are infinite. Recall that in section 3.5, limits at infinity, when we looked as x was going towards infinity and we had our exponent rules. We've looked at that before. The definition of improper integrals with infinite integration limits. Number one, if f is continuous on the half-open interval from a to infinity, the half-open interval, closed at a, open to infinity, then from a to infinity, the integral of f of x dx is the limit as b goes to infinity from a to b, f of x dx. So we'll take our limit as b goes to infinity. If f is continuous on the interval negative infinity to b, closed at b, then the integral from negative infinity to b of our function f of x dx is defined to be the limit as a goes to infinity from the interval a to b f of x dx. The above improper integrals, both of these, are convergent if the corresponding limit exists, and they are divergent if the limit does not exist. If f is continuous on the interval negative infinity to infinity, then the integral from negative infinity to infinity of f of x dx is the integral from negative infinity to c of f of x dx plus the integral evaluated from c to infinity of f of x dx. The above improper integral right here on the left side of the equation diverges if either of these improper integrals on the right side diverges. And this integral converges if both integrals converge. These are two very important facts that you need to know. Now it says here to look at examples 1 through 5 on pages 579 to 581 for examples of these types using these properties. So be sure that you turn in your book now and look at those. We'll talk about them in class, but I want you to have looked at them before we talk about them. So we are going to evaluate from negative infinity to 0 the integral of x times e to the x dx. So first of all, we have an improper integral because of this right here, so we have to rewrite our integral as a limit. We're going to talk about the limit as a goes to infinity of the integral from a to 0 of x times e to the x dx. Now what we have here is integration by parts, and we have actually done this one before. So integrating by parts, we recognize our u is going to be x, our dv is ex. So the integral of u dv is uv evaluated from a to b minus the integral of a to b v to u. So we have our u and dv, our du and v. So our integral is going to become, here's our u times v evaluated from a to 0 minus the integral from a to 0 e to the x dx. Now we know how this integrates, so that's nice and easy. So 0 times e to the 0 minus a times e to the a. That's our fundamental theorem of calculus here. And now minus, and we're going to evaluate e to the x from a to 0. And we get this. Now this is just part of the problem. We haven't taken our limit yet. We still have to do this. So let's think about what negative a times e to the a is. Our limit as a goes to infinity of a times e to the a would be on top. We could write e to the a as e to the negative a on bottom. Now, why would I want to do this? This puts us in a situation where the top goes to infinity and the bottom goes towards infinity. So we have a L'Hopital's rule, actually negative infinity, okay? And we have a L'Hopital's rule situation. So the derivative of a is 1. The derivative of e to the negative a is negative e to the negative a. And so the limit as a goes to negative infinity is negative e to the a. We substitute negative infinity there, okay? Which is 0. This is negative e to the negative infinity. Of course, we don't write that, but that would be 1 over e to the infinity, which is 0. Okay? So now let's look at our actual integral. From negative infinity to 0, the integral of x e to the x dx is limit as a goes to negative infinity, this whole quantity here. And we have already evaluated that the part where it's a e to the a is 0, so negative a e to the a is still 0 times negative. This is a constant. Limit of a constant is the constant as a goes to negative infinity. And then as a goes to negative infinity here, we would have, of course, 1 over e to the infinity, which again is 0. And there is our limit. Now let's remember that we have here these ideas. The limit as a goes to negative infinity of a would be negative infinity. The limit as a goes to negative infinity of e to the negative a would actually be infinity. So you have to think about those things. The second basic type of improper integral is one that has an infinite discontinuity at or between the limits of integration. So the definition of improper integrals with infinite discontinuities is if f is continuous on the half-open interval from a to b, closed at a, open at b, and is discontinuous at b, then the integral from a to b of f of x dx is the limit as c goes to b from the left of a to c f of x dx if this limit exists as a finite number. Now, why are we approaching b from the left? Because it is the half-open interval, and we have to approach b from the left side because it's not closed at b. If f is continuous on the half-open interval from a to b, open at a, closed at b, and discontinuous at a, then the integral from a to b of f of x dx is the limit as c goes to a from the right. Again, not closed at a, have to approach from the right side. As c goes from a to the right, the integral from c to b, f of x dx, if that limit exists and as a finite number. Now, in examples 1 and 2, the improper integrals are convergent if the corresponding limit exists and divergent if it does not. If f is continuous on the closed interval a to b, except for some c in that open interval a to b, at which f has an infinite discontinuity, then the integral from a to b of f of x dx is from a to c f of x dx plus from c to b f of x dx. In number 3, the improper integral on the left side of the equation diverges if either of these improper integrals on the right side diverges. Evaluate the integral from 0 to 1 of natural log of x dx. Now let's remember this is from 0 to 1 natural log of x times 1 dx because we know we're going to have to integrate by parts. So our u is natural log of x, our du is 1 over x dx. That makes our dv dx and our vx. So the integral from 0 to 1 of natural log of x dx is the limit as c goes to 0 from the right side of c to 1 natural log of x dx. Now, integrating by parts, here's our u times v from c to 1 minus the integral of v du from c to 1. Now, we can integrate this very nicely. This becomes x. So now we're going to evaluate this part from c to 1 using fundamental theorem and this part from c to 1. Right? Substituting 1 in minus substitute c in minus substitute 1, substitute c. So when I do all the simplifying here, I get negative c times natural log of c minus 1 plus c. Now, if I use L'Hopital's rule, I know that, let's just look at c times natural log of c. I could write this as natural log of c divided by 1 over c. And as we go to 0 from the right side, natural log of c goes to negative infinity, 1 over c goes to positive infinity. And so I have L'Hopital's rule applies because I have indeterminate form. So this becomes, taking derivative, 1 over c. This becomes negative 1 over c squared. And this simplifies to the limit as c goes to 0 from the right of negative c, which is 0. Therefore, the integral from 0 to 1 of natural log of x dx is the limit as c goes to 0 from the right of this quantity, and evaluating that as c goes to 0 from the right gives me negative 0 minus 1 plus 0, which is negative 1. Now I want you to look at examples 6 through 10 on pages 582 and 583 for more examples of this type. Also, see the rule for special types of improper integrals in the blue box on page 584 and example 11 on page 584 for a more in-depth example. Now, these examples are actually in this lecture manual on the next few pages. Your TPs are numbers 5, 15, and 17. See you next time.